is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today, I am going to discuss with you regarding binary search trees. Okay, so in my previous video, we have discussed about what a binary tree is and the traversal techniques in a binary tree. So, binary search tree is a version of binary tree where the constraint of having only two children at max prevails. Right? So, let's look at this hierarchy. First of all, before going in depth into binary search trees, have a look at this one. A tree. What is a tree? A tree is the one which have a root node. Okay, so starting from the root node, you can have any number of children. To that, you can have any number of grandchildren, and so on. It is going to stretch itself in downward direction to any length. Root node is the only node which do not have any parent. So if you want to perform a search operation, insertion operation, or deletion operation, you have to start with the root node. There are no restrictions on general trees. It can have any number of children. But storing data in such type of trees, free trees, there will be a constraint saying that, so traveling, how to traverse. We do not know how many children a node have. So we do not have boundaries. So to overcome that, or to put a boundary to limits to this tree, non-linear data structures, they have come up with binary trees, where they have kept a constraint saying that a node can have a maximum of two children. If a node have two children, can we categorize saying that the root have a left child and a right child, and the left child have another left child and a right child? So the two directions are defined. When we put a constraint that a tree can have only two children at max, it can even have a single child also, as I have shown in this figure. The last node, it can have a single child, right? So this is the advantage with the binary trees. So we do not have any constraints, right? So happy with that. We do not have any constraints on the data which we store, but the number of children constraints or traversal will be easy. Further in the future, they have come up with few constraints saying what is the order, in which order data is stored. That is also a hectic problem, right? So they have come up with two different types of binary trees. One is heap and the other is binary search trees. So both are versions of binary trees, heaps as well as binary search trees. Then what kind of constraints they have imposed? Let's have a look at this one. So heaps can be called as max heaps or min heaps as well, right? So if the parent value is less than its children, then it is known as min heap. If the parent value is greater than its children, it is known as max heap, right? So that was one of the constraints. The second binary version of binary tree is binary search tree. So binary search tree, they have kept a constraint in such a way that the left children will have a value less than or equal to its parent, whereas right child will have a value greater than its parent. So have a look at this picture. If K is the node, then its left children values will be less than or equal to K, whereas right children values are greater than K. So this worked a lot when they stored data. The in-order traversal of binary search tree gives you the data in ascending order, which was highly beneficial because sorting the data using a non-linear data structure is not a silly task. It is a highly tedious task. But when you store the data in a binary search tree and get the in-order traversal of that, you can sort the data in ascending order, which is the beauty of BSTs. The short form of binary search trees is BST. So have a look at this example. Simple example which I have taken over here. The root node is 25. Have a look at this whole diagram. Okay, each and every node have all the internal nodes. So guys, please first of all differentiate, try to understand between the internal nodes and external nodes. Let me write it. Nodes can be classified into two categories, internal and external. Internal nodes are the nodes who have either one or two children, whereas external nodes have zero children. This is based upon the children I'm going to classify them. Okay, so here 25, 20, 36, 10, 30, 40, 5, 12, 48 are internal nodes because these nodes have either one child or two, right? Coming to your 1, 8, 15, 22, 28, 38, 45 and 50, they are known as external nodes because they don't have children, neither left nor right, right? They are also known as leaf nodes. Okay, they are also known as leaf nodes. Okay, coming to the nature of the data within the nodes. Have a look. All the elements which are present in the left subtree of 25 are having a value less than 25. Whereas all the elements which are present in the right subtree of 25 are having a value which is greater than 25. Right? The same property prevails till you reach the leaf nodes. Take a random node, say 10. Okay, so its left subtree is headed by 5, right? So all the elements which are left to 10 are smaller than 10. Coming to all the elements which are right to 10 are greater than 10. This property of BST prevails with till the leaf node. All the internal nodes must abide to this property, where the left children are less than the parent and the right children are greater than the parent. By this, I hope you understood what a BST means first of all and what will be the nature of data in a BST, right? Then what are the basic applications? So as I said, the in-order traversal of BST gives you the ascending order, data in the ascending order. They will be helpful in representation of arithmetic expressions and be used in Unix kernels for managing the virtual memory. Virtual memory areas will be the data which is present in virtual memory will be stored in the form of binary search trees. So these are the major applications of your binary search tree. So what are the basic operations that can be performed on a binary search tree? Basically, 3 operations you can perform. One is to search, the other is to insert and delete. As in all the 3 operations, remember guys, in all the 3 operations, we have to start from the root, and in search, we are going to search till the leaf nodes if we do not find the element within the internal nodes. So that's why even in insertion, you have to check for the right position of the element, right? So the time complexity for search, insertion as well as for deletion is order of log n. We go off log n time complexity. It is very less when compared to linear ones. And it is very easy to insert as well as delete elements. Pictorially, you might feel difficulty, but practically when you try to store data, huge data, then nonlinear data structures are very helpful when compared to linear ones. Right? So let's have a look. So insertion operation. Right? So remember one thing, we are going to insert an element in a binary search tree always at the leaf node. always the new element is going to come and sit as a part and parcel of the leaf node set. Okay, so if the first node which you are going to create, you are going to insert is the first element, that is the tree is not yet being started or constructed, then that becomes the root node by default, right? So that means if the tree is empty, make the first node as the root node. If the root node is not empty, comparison starts, my dears. Compare the new element which you want to insert. Is it less than the root node or greater than the root node? If it is less than the root node, then it clearly tells you that it is supposed to be on the left hand side of the root. So travel towards the left. If the element which you want to insert is greater than the root, then travel towards the right. Because as it is right, BST property tells that higher element should be present in the right hand side, right? So push it to the right hand side. So recursively use the same process. Compare the element with the root of the subtree, and if the value which you want to insert is less than, send it to the left. If it is greater than, send it to the right. Repeatedly you are going to do unless you reach the leaf nodes place. Once you reach the leaf node space, place it, push it, right? So this is in short your insertion operation, which I am going to explain you using a tree. Let's have a look at this one. Let's construct a binary search tree for the given list. Have a look at this one. The elements are in random. They are neither in ascending nor descending order. 8, 3, 10. That itself tells you. Okay. The first node, what did I tell you? First node always behaves like the root node, right? As initially the tree is empty, the first node will be the root node. After 8, what is the element that you have to consider? 3. So 3. Compare it with 8. Is it less than 8 or greater than 8? As it is less than 8, we have to insert it into the left subtree of 8. Right. Now, it is the left child of 8. The next element is 10. Again, start comparing with the root node first. Is 10 greater than 8 or not? As it is greater than 8, it is going to come and sit as the right child of 8. As right child position of 8 is empty, you can definitely place it. Place it. Right? Next comes the value 1. Again, start from the root. The value of 1, the value which you want to insert, is less than the root. So travel towards the left. In the left, vacancy is not there. You have an element 3, right? So compare 1 with 3. As the value 1 is still less than the node which you have, so it should be present in the left subtree of 3. As it is supposed to be in the left subtree of 3. Is 3 having any left subtree? No, it is not having any left subtree. So make it as the left child of 3. So I made 1 as the left child of 3. So guys, have a look at this one. Whatever the element I am inserting it is getting settled as a new leaf node. Okay. So in BSTs, the newly inserted element will always be inserted in as a leaf node. Okay. Come back to our question. The next element to be considered is 6. Let's start the process. So start with the root 8. 8 compare with the element which you want to insert. 8 is greater. So move towards left. The left space is not empty. You are having 3. Compare it with 3. So our element, the element which we want to insert, is greater than 3. Mane, the new element is going to go to the right hand side of 3. So is there any element present in the right hand side of 3? No, there is no element. So I can place it as the right element of 3. So 6 becomes the right element of 3. Next comes 14. Let's start the same process. Start with the root node. As 14 is greater than the root node, travel towards right. Do you have an empty space there? No. 10 is there. Compare it with the element which is in your hands. So 14 is greater than 10. That means you need to push it to the right hand side direction of 10. Do you have any element to compare in the right side of 10? No. So introduce 14 as the right side of 10. So guys, see, every element is a new leaf node. Okay. Next element to be considered is 4. Right? Compare it with the root node, which is 8. Once I compare it with the root, I can understand that it is smaller. So I have to travel towards left. Once I travel towards left, in the left subtree, the element 3 is present because the left subtree of 8 is headed by 3. Compare it. You can clearly see that 4 is greater than 3. So travel towards right. Right, an element is already present, which is 6. Compare 4 with 6. 4 is less than 6. That means it is going to definitely come and sit in the left hand side of 6. Do you have any element in the left hand side of 6 to compare? As we do not have, introduce it as the left child of 6. Right? So the new leaf that comes into the picture is 4. Next element, 7. Start the same. As I said in the first slide itself, in trees, whether it is search, insert or delete, you have to start with root. The only address that we have in our hands will be the address of the root. Yes, let's compare. Compare 8 with 7. 7 is lesser. So, left hand direction. Compare with 3. Greater than 3. So, right hand side direction. Greater than 6. So, right hand side direction. As 6 is not having any right child, introduce that as a new right child. Okay. This is how 7 is inserted. Okay. Then the last element, which is 13. When we compare 13 with 8, we can clearly see that it is greater. Let's travel in the right direction. 10 is present. As 10 is present, we can clearly see that 13 is greater than 10. Let's further go deep in the right side. 14 is present. Compare with 14. But 14 is greater than 13. So clearly it tells you that 13 must travel towards the left side of 14. But do you have any element in the left hand side? As we do not have any element in the left hand side, introduce 13 as the left element of 14. Have a look at the final BST, guys. My list is over. List of keys is over. This is the final BST which I have constructed with the list of the elements. Right? So the BST property, that is left child must be less than the parent and right child must be greater than the parent, prevails for each and every node, every internal node. Okay? Let me explain you with another example, guys. Here now I have taken a huge one. Initially the tree is empty, right? So the first node becomes the root node. So 25 is the root node. Next element is 50. Compare with the root. So as it is less than 25, it is going to come as the left child of 25. Next element to be considered is 50. Compare it with 25. As it is greater, send it to the right. Right? Next element to be considered is 10. Compare with it 25. Lesser, left hand direction. Compare it with 15. Lesser, left direction. As there is no left element for 15, introduce 10 as the left child of 10. Okay. Next comes the element 22. Right? Compare it with 25. That is the root. As it is lesser, left hand direction. Compare it with 15. As it is greater, go towards the right direction. Do you have any element as the right child of 15? No. So introduce it as the right child of 15. Next element that comes into the picture is 35. Right? So coming to 35, as it is greater than 25, travel towards the right hand side. Compare it with 50. But when we compare, it is less than 50. So travel towards the left. But do you have any element in the left? No. So introduce 35 as the new left element of 50. Next element that is in our hands is 70. Compare it with the root. So as it is greater than the root, travel towards the right. Compare it with 50. 70 is greater than 50 also. You have to travel towards the right. But do you have any element in the right? As we do not have any element in the right, introduce it as the new element, right element of 50. Next element to be considered is 4. Right? So compare it with 25. As it is lesser, travel towards left. Compare it with 15, lesser. Travel towards left, compare. As it is lesser, travel towards its left. But when you travel towards its left, you do not have a left subtree for the same. So introduce 4 as the left subtree of 10. Right? So the next element, which is 12, again start the same process. Start comparing with 25. As it is lesser, travel towards its left, compare with 15. Lesser, travel towards its left, compare it with 10. Greater, travel towards its right. But as we do not have any right child for 10, introduce it as the new right child of 10. Next element to be considered is 18. Start comparing with the root. Lesser, compare with 15, greater, compare with 25, lesser. So introduce 18 as the left child of 22. Okay. The next element is 24. Compare it with 25. So as it is lesser, travel towards left. Compare it with 15. Greater, travel towards its right. Compare it with 22. It is greater. So as there is no right child for 22, introduce it as the new right child. Next element to be considered is 31. Okay, so as 31 is greater than 25, travel towards right. Compare it with 15, it is less than 15, travel towards its left. Compare it with 35, it's lesser. Travel towards the left, but there is no left child for 35, so introduce 31 as the new left child of 35. Next element is 44. Compare 44 with 25. As it is greater, travel towards right. Compare it with 50, lesser, towards left. Compare it with 35, greater, travel towards the right. But as there is no right child for 35, introduce 44 as the new right child. Okay, nice. Job done with 44, guys. 2 more elements left. Next element is 66. Compare it with 25. Greater. Compare it with 50. Greater. Still right. Compare it with 70. Lesser. That means left side. Do you have any element in the left side of 70? Make 66 as the left child of 70. So guys, have a look. We are introducing every new element, inserting a new element as a leaf. Last element is 90. Compare it with 25. Greater right side. Compare it with 50. Greater right side. Compare it with 70. Greater right side. Do you have a right child for 70? If you do not have any right child for 70, introduce 90 as the new right child. Right? So there ends my list and there completes my construction of binary search tree. Have a look at this final tree. Have a look at this one. The BST property, binary search property, which says that left child must be less than the parent, whereas right child must be greater than the parent, prevails. You take any subtree random. Let me take this subtree. 50 ka subtree, right? All the left children of 50, that is left subtree of 50 is having the values 31, 35 and 44. All are less than 50. The right children of 50 are 66, 70 and 90 and they are greater than 50. Right? You can look at and compare with any node you want, guys. So let's have a level 2 node which is 22. Then its left child is 18 which is less than 22 and the right child element is 24 which is greater than 22. Right? So the BST property prevails and this is a process of insertion or you can say construction of a binary search tree. This you can go it to any extent. Let me take a random example as 53 where you are going to insert it. Okay, so compare it 25 greater. So go to the right side. Compare it with 50 still greater. Go to the right side. Compare it with 70. It is lesser. Go to the left hand side. Compare it with 66. Lesser. So 53 settles as the left child of 66. Am I right? So in this way you can extend it to any length. Let me take another example. A simple one. Okay, compare it with 25. Lesser. Compare it with 15, lesser, left hand. Compare it with 10, lesser, left hand. Compare it with 4, lesser. Do you have any left child for 4? No. So, introduce 1 as the left child for 4. So, in this way, you can see that first point is the BST property, that is left and right child's nature properties prevailed. Second point, every newly inserted element settles as a leaf node. Newly inserted element settles as a leaf node. Okay, this is how we construct a binary search tree. Let's look at the deletion process. Okay, so deletion. We have 3 cases in case of deletion ideas. Case 1. A case where you are trying to delete a leaf node. A leaf node is a node which has no children. Am I right? So if you remove that, will the order or the structure of your tree is going to get disturbed? No way. So it's a very simple one. Okay. Next one with the single child. That means a node which have either a single left child or a right child. What to do? That means if you remove that, the link between the child and grandparent is going to break. If you remove the parent just like that, we cannot do that. It is having a small algorithm which will explain. You have to delete a node with a single child. Second with 2 children. Right? You can have a node with 2 children. And if you are supposed to delete it, how you are going to handle the situation is the point. Right? So these are the 3 cases when we delete a node from a binary search tree. Let's start with the least complex one, which is deletion of a node with no children. That is deleting a leaf node. Have a look at this picture. And there are two steps simply. Find the node which you want to delete. If it is a leaf node, simply remove it and terminate the function. For example, have a look at this picture. What if I want to remove 7? First of all, check, is it having any children? Is 7 having any children? No. 7 is a leaf node. Simply remove it. Is the structure of your BST got disturbed? Nahi na? So no problem. So when you try to remove an element with no child, then there will not be any problem by removal. For example, say if you want to remove 1. If you remove this one, is the structure of your final BST is going to change? No. Right? So there is no problem. Second case, as I said, what if you want to remove a node with a single child? Have a look at this picture. What if I want to remove 10? If I blindly remove 10, the link between 8 and 14 is going to break. That is, the relation between the grandchild and child is going to break, which I cannot do, which literally means losing the data. Right? We cannot lose the data at any cost. Right? So have to make sure that data is not lost, as well as the property of BST is prevailing. Right? So have a look at this algorithm first of all. Search for the element and check whether it is having no child, single child, or 2 children. So if it is having only 1 child, it can be left or right. भैया कोई भी बच्चा एक हो, बस एक ही है, ठीक है? So left हो या लड़का हो या लड़की, एक ही है बस. In that way, you can think. No, left children will be given priority, right? And think of sort like that. Okay, the formula is the same for all, right? If you find that the element which you want to delete is having only 1 child, then construct or create a link between its parent and child. Create a link between, as you have seen, I have marked it very clearly. I have created a link between grandparent and the child and deleted or feed the node and terminate the function. Let's have a look at this one. If you remove 10 from the picture, so 14 becomes the child of 8, a right child of 8. 11, which was the left child of 14, will remain the same. There is no change in that. There is no change in the property of 11. But a new structure will be formed where 14 becomes the right child of 8. Okay. Let's have a look at another example. In this given picture, what if you want to remove 6? 6 is having a single left child, right? What if you want to remove this one? If you want to remove this one, what you have to do? Who is the parent of 6? 3. Who is the child of 6? 4. Build a relation between them and remove 6. Got it? So as we all know that as the right subtree of 3 will have all the values which are greater than 3, 6 ho ya 4, there will not be any violation of rule of BST, right? So I've just built a bridge between the parent of 6 and child of 6 and 6 quit from the picture. So have a look at the final one. Now the right child of 3 is 4, right? So the BST property prevails, there is no imbalance, and deletion process is also a success. Okay, let's look into a case where you are trying to remove a node with 2 children. Yeah, this is a tedious one. Please pay some attention. Okay, so search for an element. And if the element is found and it is having 2 children, that you have to adopt one of the steps. One is choose its successor. Choose its successor. Where the successor is found. That is the primary question. It is the leftmost element of the right subtree. Remember, it is the leftmost element of the right subtree. Or you can even replace it with predecessor. Predecessor is nothing but rightmost element of the left subtree. Why I am talking like this, predecessor, successor words? Why? Because we all know that the in order of BST will give you ascending order. Right? Am I right or wrong? So if you want to remove an element, from a list, right? Its predecessor is the value which is less than it within the list, just a step left to it, and its successor will be the element which is higher than it and which is next to it, right? Which can replace or which can justify the position of the element which we want to remove. That's why I told you in order traversal technique is very, very important. Guys, you can go through my previous video to understand how to write the in order traversal of binary trees. Okay. Yes, come back to our process. So, first of all, once you find that the node which you want to remove is having two children, adopt one of the process. One is to identify the successor or predecessor. Replace the element which you want to delete with its successor or predecessor and remove the element, free the element. Okay, remove or free the element. Let's have a look at an example of these two. Have a look at this tree. This is a binary search tree where all the left elements are smaller than its parent and right children are greater than its parent. Now I want to remove 3. What is the basic position of 3? Have a look at this one. 3 is the head in 3 is actually heading the left subtree of 8, which is having a tree-like structure, subtree-like structure with left and right children. Both the children are there. Right? So we can replace it with, what did I tell you? If you write the in order of this subtree, guys, try to write the in order of this subtree. So what will be the in order? 1, 3, 4, 6, and 7. Okay, I have written the in order of only the subtree, left subtree, which is of my point of concentration, because I have to remove 3 and replace it with suitable element. Right? So when I remove 3, I can either replace it with 1 or 4. Right? So right now I have chosen the successor element 4. Once I replace it with 4, have a look at the picture next to it. So what it is saying? So the element 4 have overwritten the value 3, right? And remove the element for duplicates. What is the use of duplicates? Remove this. So this is the final picture which I'm going to. 4 is sitting at the previous position of 3, and the node which is 4, which was actually the left of 6, is been removed. Right? 4 is left of 6, right? So it is been removed. So this is one process. Or you can replace 3 with either with 1. If you replace 3 with 1, you're going to remove this node. Even in that case, the BST property is going to prevail. No problem at all. Okay. Have a look at this one. This is the worst case scenario, I can say. A case where you are trying to remove the root node itself. Root node, if you want to remove, have a look at this one. This is a very structured BST which is having 2 children and 8 is having grandchildren also, right? So have to remove 8. So either we can replace it with its predecessor or successor. First of all, who is the predecessor of 8? What did I tell you? The rightmost element of its left subtree. This is the left subtree, and its rightmost element is 7. Either you can replace with 7 or the successor. That is the leftmost element of your right subtree, which is 10. Right? Either you can replace it with 7 or 10. Yes, if you get a bit of confusion, need not worry about that. Write the in order of this one. What is the in order of this one? 1, 4, 6, 7, 8, 10, 13, and 14. This is the in order. Am I right or wrong? Right? So the element which you want to delete is 8. That means you can replace it with either 7 or 10, as I said. 7 is the predecessor, 10 is the successor, right? So you can replace it with either one of them. Guys, my humble request or suggestion for you guys will be, remember one fund. Do not remember both. Okay? Either when I was studying, I used to fix my mind with predecessor. Aage wala, right? So even if you want, you can fix your mind, or if you want, you can remember both. But if you get this type of question, this type of logical question in your interviews, you need to give both the options to the interviewer, which who is going to ask you the questions, right? Technical rounds. But when you implement it, confine yourself to single funda. The process will be fast. Okay. So here in this example, I have chosen predecessor. That is 7. What will happen? Just move 7 to the root, replace 7 with 8 with 7, and remove free the node over here. Have a look at this one. Is the BST property prevailing or not? Our basic point must be, after every insertion or a deletion, BST property must be present, right? So have a look. So 7 reached at the top, that it became the new root of the tree, and new to root of the tree, and so the node, that is the right side, previously 7 was the right child of 7, is been removed. Why? To have redundant data, right? Duplicate data. So removed it, and 8 went off. It is totally been deleted, right? And look at the BST properties. As 7 is heading the tree now, all its left children are less than 7, whereas the right children are greater than 7. Did you understand the deletion? So deletion, remember guys, we have 3 cases. A case where the node which you want to remove is having no children. Second case, a case where you are trying to remove a node with a single child, whether it is left child or right side, but single child. And a case where you are trying to remove an element which is having 2 children. In case of 0 children, that is, you are trying to remove a leaf node, simply remove it, no problem. The BST property will prevail, and the structure, you are not going to lose the data also. Coming to the case of single child, to avoid losing of data, build a new relation between grandchild and the child, so that BST property will prevail and data will not be lost. Coming to the third case, where the node which you want to remove have 2 children, then choose either successor or predecessor to replace the element. Successor is nothing but the leftmost element of the right subtree, or predecessor is nothing but the rightmost child of your left subtree. Replace with either one of them, then job done. Okay, so with this note, I would like to conclude that we have seen the binary search tree, its basic applications, and the techniques with which we can search, insert, and delete nodes in a binary search tree. Thank you. Thank you for patiently listening to this one. And if you have any doubts in the prerequisites of this concept, do visit my already existing videos. There I have covered all the basics, like tree representation and what a binary tree is and its traversal techniques. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.